Welcome to a lesson with Dr. Powell. Let's take a look at finding multiplicative inverses by powers, inversion by powers, and modular arithmetic. So first, let's consider this. We're gonna find the inverse of 7 mod 17. And the way we're going to do that is remember that since in the multiplicative group, mod 17, z mod 17z, but then we're looking at just the elements that have inverses. There's 16 of those because 17 is prime, and there's 16 numbers 1 through 16 that have that do not share any common factors other than 1 with 17. So 7 to the 16th will be equivalent to 1 mod 17. Well, that actually gives us something great. That means 7 to the 15th is the inverse. And in general, a to the Euler phi function of n, which is the number of elements in the multiplicative group, minus 1, it will be the inverse. So how can we use that to our advantage? Well, we have a specific power that will always yield the inverse. So instead of using other techniques, this is an alternative. It's not always the fastest, but sometimes it is. Sometimes it works great. So we present it as an alternative here. In this particular case, maybe this could be done faster to find the inverse. However, it's not too bad. So what we do is we know 17 to the 15th power, or 7 to the 15th power will be an inverse mod 17. So to be able to compute this quickly, we'll write 15 in base 2. So the way we do that, we recognize it's odd, which means in the ones place of base 2, there'll be a 1. Then to move to the next place, what we do is, well, we take that 1 away and we divide by 2 and see if it's odd or even. If it's odd, we put a 1 in the next place, right here. Okay, then we take that 1 away here and divide by 2 and you get 3. See if it's odd. It is, so we put a 1 there, and we divide by 2 again, and after we subtract 1, we get something odd, so we put a 1 there, and the last place, then we end. So if we ended up getting an even number when we divided by 2, then we would just put a 0, and then instead of subtracting 1, we just divide by 2 at that point. Nonetheless, we can quickly obtain the base 2 representation for a number without too much trouble. Then from there, we can just list out powers of 7. We go 7, and 7 squared is 49, but 51 is a multiple of 17. Multiply by 3, get 30 plus 21. Okay, so, and it's 2 less than that. That's great. So we can say, so 7 squared is -2, and that's not a nice reduction because then we can square easily from there to 4. And then 4 squared is 16, which is -1. And we end there. We have the list starting from the 1's place, the 2's place, the 4's place, the 8's place, and then we end. And see these 1's, this means that we're going to multiply all of these together. If there was ever a 0, then we don't multiply that one, we skip it over and we just do that times, and we go to that place. Okay, so we know actually so the result is actually going to be just these guys multiplied together. And now to simplify things a little bit, 7 times -2 is actually -14, which is the same thing as 3 mod 17. 4 and -1, that's -4. Multiply those together to -12. And 17 minus 12 is 5. So 5 is the multiplicative inverse. And so we have 7 times 5 is congruent to 1 mod 17. You can check it. 35 is 1 more than a multiple of 17. Now, this probably could have been done another way, but nonetheless, it works. It's foolproof. As long as we know the Euler phi function of a number, we should be able to, which is obtained by knowing how it factors, you should be able to find the inverse of a number mod in a mod. Thanks for watching.